Hello friends. So today we are going to discuss questions from heat and thermodynamics, and these questions are from the year 2021, and we are going to discuss 15 questions, and all these questions are from the mains. And for the year 2021, this is part 2. Okay, the part 1 also we discussed some of the questions from the year 2021, and those questions were also from the mains. First question, it states that a reversible heat engine converts 1/4 of heat input into work. When the temperature of the sink is reduced by 52 Kelvin, its efficiency is doubled. The temperature in Kelvin of the source will be. So in this case, we are given a reversible heat engine, or we can say reversible Carnot engine, and for that we can write, or the efficiency can be written for the Carnot engine in terms of two different formulas. One is giving the temperature and other one is with respect to the work done as well as the heat. So we write both the formulas. So you know that efficiency of a heat engine, which is nu, and that is equal to W upon Q1. And here this W is the work output and Q1 is a heat input. Okay, and we are given that it converts 1/4 of the heat input to the work. So we are given that our work, that is W, is equal to 1/4 of heat input. Therefore, we can write that W upon Q1 is equal to 1/4, and this is nothing but our efficiency. Okay. And now we can use the other formula of efficiency, which is with respect to the temperature. Okay. In this case, we are given the reversible Carnot engine. So we have reversible Carnot engine, and its efficiency will be equal to 1 minus T2 upon T1. Here our T2, temperature T1 is our source temperature, and T2 is our sink temperature. And in this case, we can substitute value of efficiency, which is 1/4. So we get this as our 1/4 is equal to 1 minus T2 upon T1, and this gives us that our T2 upon T1 will be equal to 1 minus 1/4, which is giving us 3/4. So we can say our T2 is equal to 3/4 times T1. And now in the second case, it says that sink temperature reduced by 52 Kelvin. So we are given that our sink temperature is reduced by 52 Kelvin. So we can say that our new sink temperature let us call this as T2 prime will be equal to T2 minus 52. And it also states that our efficiency is doubled. So in the first case the efficiency was 1 by 4. Therefore we can write that our new efficiency is doubled. New efficiency is doubled, which can be said by new prime is equal to 2 times new, which comes 2 times 1 by 4, giving us 1 by 2. Now we can use once again the formula for our efficiency with respect to the temperature. So we can say our new efficiency will be equal to new prime is equal to 1 minus T2 prime upon T1, and efficiency is 1 by 2. Therefore we can say that our T2 prime T1 will be equal to 1 minus 1 by 2, which will be equal to our 1 by 2. And we can substitute our T2 prime as T2 minus 52. So from here we get T2 minus 52 upon T1 is equal to 1 by 2. And we also know that our T2 is equal to 3/4 of our T1. So we get this our 3/4 of T1 minus 52 oblique T1 is equal to 1 by 2. So from here we can easily calculate our T1. And we can just make some adjustment here. So we can just, you can say, segregate T1 with respect to our numerator. So this will be our 3/4 minus 52 upon T1 is equal to 1 by 2. And from here we get 52 upon T1 is equal to 3 by 4 minus 1 by 2. 4 will be LCM, and this will be coming as our 2, and this will be 1 by 4. Therefore we can say that our T1 will be equal to 4 times 52, which comes as 208 Kelvin. So the temperature of the source will be 208 Kelvin. Next question. It states that the temperature theta at the junction of the two insulating sheets having thermal resistances R1 and R2, as well as top and bottom temperatures theta 1 and theta 2 as shown in figure is given by. So we have to find out the temperature at the junction in terms of theta 1 and theta 2 as well as the thermal resistance. So in this case, as normally these type of questions, we assume that there is a steady state heat flow. Therefore we can say that the heat current, which is H, is same through the both. So you can say for steady state heat flow the heat current H is same through both. Same through both. So it means that the heat current associated with this lower one will be also H, and the upper one will be also H. So we can write the heat current H with respect to upper layer as well as the bottom layer. Okay. Therefore, we can say that our heat current, which is our H, it can be written as theta 1 minus theta upon R1, and that will be also written as our theta minus theta 2 upon R2. And now it is quite simple to solve. We can just cross multiply them and we get this as our R2. Theta 1 minus theta is equal to our R1 theta minus theta 2, and we can take theta as common, or we can say theta to one side, so that will be giving us R2 theta, or we can say R1 theta plus R2 theta, and that will be equal to R2 theta 1 plus R1 theta 2. One second. So this is our this is theta. Okay, and this comes as our R2 theta and R1 theta, and we are left with this will be equal to our R2 theta 1 minus R1 theta 2. One second, let me open it. There is slide. Not sure where the problem lies, so let us R2 theta 1 minus R2 theta is equal to R1 theta minus R1 theta 2, and we can combine these two terms. So this comes R1 theta plus R2 theta, and it will be equal to R2 theta 1 plus R1 theta 2. Okay. And from our left side we can take theta as common, and that will be equal to our R2 theta 1 plus R1 theta 2 divided by R1 plus R2. So we have this as our R1 plus R2 in the denominator, and we have option number 3 is correct. Theta 1 multiplied by R2. Theta 1 multiplied by R2. So we have option 3 is correct. Next question. It states that in a mole of a perfect gas, it should be n mole. Okay, we'll say that later on. Undergoes a cyclic process ABCA, see figure, consisting of following processes. A to B is isothermal expansion at temperature T, so that the volume is doubled from V1 to V2, which is equal to twice of V1, and pressure changes from P1 to P2. B to C is isobaric compression at pressure P2 to initial volume V1. C to A is isochoric change leading to change in pressure from P to P1, the total work done in the complete cycle ABCA. So basic figure is given to us. It starts from A and it is our isothermal expansion A to B. Then B to C is our B to C is our isobaric compression, and C to A is our isochoric. Okay, it means volume is constant. And so we are interested in finding out the work done. So in order to find out the work done, we will just take the processes one by one, and let us start with our AB, and AB is given to us as isothermal expansion. So we have our A to B, and that is our isothermal expansion. And so we start with our ideal gas. So we know that for ideal gas, PV is equal to nRT. And number of moles is about 1, and we are given that our initial is given to us as P1 V1, and we are given as final is our P2 V2 with our V2 is equal to twice of V1. And then we can use our so we can start with our for temperature constant. We can write that for isothermal, we can say that our P1 V1 is equal to P2 V2, and in place of our P2 we can put our P1. Therefore we get the P1 V1 is equal to P2 and twice of V1, and here V1 cancels out, so we get that our P2 is equal to P1 upon 2. So we got the relationship between our pressures, and now we can use our work done formula. So we can say our work done for AB, we can write this as WAB, which will be equal to nRT and natural log of V2 upon V1. So now we can easily substitute our V2 and number of mole is 1, so this comes as our RT natural log of, and V2 upon V1 will be equal to 2, so we can substitute here 2. And now we come to our next, which is our BC. BC is our isobaric compression. And for isobaric compression, we are given that pressure is P2, which is equal to our P1 divided by 2, and the volume is, it changes back to V1. I think it changes back to V1. Yeah, it changes back to V1. So we have our V2, which was equal to twice of V1, and it changes back to V1. So we can use the basic formula for work done for BC. So we can say our work done for BC is equal to our P2, and this comes as our V1 minus V2. So this comes as P1 by 2, and we get this as V1 minus twice of V1, which will be giving us minus of P1 V1 divided by 2. And this we can write in terms of temperature, because everything is in terms of temperature. So we know that our P1 V1 will be equal to our RT, because N is 1. Therefore we can write that work done for BC will be equal to minus of RT divided by 2. Now we come to our CA, which is isochoric, constant volume. So work done will be equal to 0. So we have our C to A, which is isochoric. Therefore WCA will be equal to 0. And now we can find out a total work done. We can say total work done, that's W, will be equal to work done for AB plus work done for BC plus work done for CA. And we simply plug in the values. We get the above work done will be equal to, this is our RT natural log of 2 minus RT by 2, and this comes plus 0. So this will be equal to our RT, we can take common, and we get this as natural log of 2 minus 1 by 2. And natural log of 2 minus 1 by 2, option 4 is correct. Okay, one second. Okay, in this case I treated number of moles as 1, but they are not 1 actually. That was mistake on my part. But I simply multiply by n. Nothing else is going to change. And next question. So we get this as option 4 is correct. 4 is correct. Next question. It states that a gaseous cyclobutane isomerizes to butadiene in a first order process which has a K value of 3.3 into 10 to the minus 4 per second at 150 degrees centigrade. The time in minutes it takes to isomerization to proceed to 40% of to completion at this temperature is. So in this case, okay, basically this question is not for here, but I mistakenly copied it. So I'll just try to solve it. And this here I'm going to use the formula for our first order reaction. So we know that our first order reaction, and that is given as natural log of our A naught divided by A, which is equal to our K times T. And it says that there is a 40% of completion, so it means 60% is remaining. Okay. So we are given that we have a 40% of completion, so which means that 60% of reactants remain. Therefore, we can write that ratio of our A upon A naught will be equal to 0.6. So we substitute in the formula. Here we get our natural log of this will be equal to 1 by 0.6 times Kt. And value of K is given to us. We need to find out a time. So this natural log will be giving us a value of 0.5108 is equal to K is our 3.3 into 10 to the power minus 4 times T. So from here we get T will be equal to 0.5108 divided by 3.3 into 10 to the power minus 4. And we get this T will be equal to 1547 seconds. But we need to find out in minutes. So we simply divide it by 60, and this comes approximately equal to 26 minutes. So we get this as our 26. Next question. It states that if 1 mole of ideal gas P1V1 is allowed to expand reversibly and isothermally A to B, its pressure is reduced to 1/2 of the original pressure. See figure. This is followed by a constant volume cooling till its pressure reduced to 1/4 of initial value B to C. Then it is restored to its initial state by reversible adiabatic compression C to A. The net work done by the gas equal to. So basic PV is given to us. So we start from A to B, then it comes to B to C, and again C to A, and various values of pressure as well as the volumes are given to us. Okay. So our A to B is our isothermal. Okay. So we start from there. We are given that we have our A to B is isothermal, and we are given that at A we having pressure of P1 and at B we are having pressure of P1 by 2. Therefore, we can say that the ratio of pressure at A, let's take reverse, ratio of pressure at B upon A will be equal to 1 by 2. And as it is isothermal process, so we can simply write our PA VA is equal to PB and VB. And from here we can say that our VB is equal to PA VA upon PB. And volume is VA is our V1. Okay, so we simply substitute it. We get that our VB is equal to VB is given to us. Anyways, I just calculated, it is not a big problem. So VB will be coming as twice of V1. It was given, but so our work done, that is our WAB will be equal to, we have this as RT natural log of VB upon VA, and which is our, this is V1. So we get this will be equal to RT natural log of, this will be twice V1 and V1. So V1 cancels out. So this comes as our RT natural log of 2. Now we come to BC. BC is our isochoric. So the work done will be equal to 0. So we have B to C, which is our isochoric volume constant. Therefore, we can say for work done, BC is equal to 0. And so we can find out, anyways we will see later on if temperature is required or not, otherwise we will keep it as it is. And then we come to C to A, and C to A is our adiabatic, and this adiabatic we are given that PC is our P1 by 4 and our VC is same as a VB. So you can say our VC is same as a VB, which is our twice of V1, and it comes back to our A, which is P1 V1, sorry, which comes to our P1 V1. And we know for adiabatic that PV raised to power gamma is equal to constant. And we can write that our work done, for work done we can use first law of thermodynamics. So we can say from first law, we have our change in internal energy is equal to Q plus W. Adiabatic process, so Q will be equal to 0. So this will be our W, and this change in internal energy, that is our delta of U, will be equal to our N C of V and delta of T. So we can write this as our C of V TA minus TC. Okay. And here this C of V will be equal to R upon 1 minus gamma. And okay, now we will be requiring temperature, so we can just find it over here also. So we were having initial temperature TA. Okay. So we can, okay, so for that we are going to use our Isochoric, that is BC process, and from that we can find out our temperature. So we can say from BC we can write that our PB VB is equal to R times TB, and our PC VC will be equal to R times TC, and our VB and VC are same, therefore we can write this will be equal to our PC VB is equal to R times TC. So we simply find out the ratio. We can say our TC upon TB, R and R is going to cancel out, and we get this a PB by, we get this a PC by VB, and we know that our PC is our P1 by 4 and PB is P1 by 2. So we can say that we have this as P1 by 4 and this is also P1 by 2, which comes as our 1 by 2. Therefore from here we get that the ratio of TC and TB is equal to 1 by 2. Okay. And we also know that our temperature at A, that is our TA, is equal to P1 V1 upon R, and this is basically isothermal process. Therefore we can say that our TB is equal to our TA, and TC is equal to T by B by 2, or we can say that TA by 2 and TA is given as P1 V1 upon R. So this comes as P1 V1 upon 2. Sorry, P1 V1 upon 2R. Yeah. So we got the temperatures. Now we can use them in the given equation. So I have written that my TA is equal to P1 V1 upon R, and TC is my, let me write it here separately. So TA is equal to P1 V1 upon R, and my TC is equal to P1 V1 upon twice R. Okay. So here we can just substitute them in this particular equation. So we get our delta of U will be equal to, we have this as C of V is our R upon 1 minus gamma, and this comes as P1 V1 upon R minus P1 V1 upon 2R, which gives us P1 V1 R is going to cancel out throughout, and this will be equal to 1 minus gamma. Therefore, so this will change internally for Ca. Therefore, our work done for our Ca, which is our change internally for our Ca, giving us P1 V1 1 minus gamma. Now we can find out our total work done. Total work done, which is our W, will be equal to WAB plus WBC plus WCA. We substitute the respective formulas which we have just found out. So this comes as our RT natural log of 2 plus 0 plus P1 V1 upon twice 1 minus gamma. And P1 V1 we can substitute with our RT, because we know that P1 V1 is equal to RT. Therefore, we get this as RT natural log of 2 plus RT twice 1 minus gamma. So we get total work done W. We can take RT as common, and we get this as our natural log of 2 plus 1 upon 2 1 minus gamma. And okay, it is written gamma minus 1, so we can simply change it. So we get this RT natural log of 2 minus 1 upon 2 gamma minus 1, natural log of 2. So we have natural log of 2 gamma minus 1, RT is common, option 1 is correct. Next question. It states that the root mean square speed of molecules of a given mass of a gas at 27 degrees centigrade, 1 atmospheric pressure is 200 millisecond. The root mean square speed of molecules of gas at 127 degrees centigrade and 2 atm is x upon square root of 3. The value of x is. So we are given two different temperatures, and we have to find out the RMS speed at the second temperature. In the first we are given 200 meter per second speed is given. So we start with our formula for our root mean square. So we know that our VRMS is equal to, this is our 3RT and M and its square root. And in the question the pressure is initially given as 1 and in second time is given as 2, but from the equation of a VRMS we can say that our VRMS is only dependent upon our temperature. So we can divide the given formula in terms of our VRMS second ratio VRMS first will be equal to square root of temperature second and temperature first. Second temperature is 127 degrees centigrade, so that will be 400 Kelvin, and first is about 27 degrees centigrade, so that will be 300 Kelvin and square root, and this will be coming as 2 square root of 3. And so we get that our VRMS second will be equal to VRMS first multiplied by 2 square root of 3. and VRMS first is given as 200. So this comes as our 200 times 2 upon square root of 3, but this is given to equal to us as x upon square root of 3. So from here we can say that value of x is equal to 400. So value of x will be 400. Next question. It states that in a certain thermodynamical process, the presence of a gas depends on its volume as kV raised to power 3 cube. The work done when the temperature changes from 100 degrees centigrade to 300 degrees centigrade will be dash times n multiplied by r, where n is a number of moles and r is our universal gas constant. Okay. So we are given that pressure in this particular case, we are given that our pressure P is equal to K times V raised to power 3, and for ideal gas we know that our PV is equal to nRT. So we substitute P, we get this as our kV cube times V is equal to nRT. So from here we can say that our volume V will be equal to nRT upon K, and this comes as fourth root. And from here now we can also find out of P, because P and volume relationship is given to us. So we can say that our pressure P will be equal to K times nRT upon K, and this comes as our 3/4. And we can just manipulate our K. So K will be coming as 3/4, so this will be 1 minus 3/4. So we get this K will be equal to our, the power of K will be equal to 1/4 times nRT whole raised to power 3/4. So we know our equation for our pressure as well as our volume, and we are supposed to find out the work done. And so we can say our work done W will be equal to integration of our V1 to V2 PdV, and we substitute our pressure. So this get a V1 to V2 K times V cube derivative of V, and so we get this as, it will be equal to K/4. We can take as common, and this will be our V24 minus V14. And we already know that our V is equal to, once again, V raised to power 4. We already know is equal to our nRT upon K. nRT upon K. So we can write this in terms of two temperatures is 100 and 300. So we can say our V1 raised to power 4 is equal to nR T1 upon K, and we can write our V2 raised to power 4 is equal to nR T2 upon K. So we substitute it, and we get our work done is equal to K upon 4, and nR K we can take as common, so So this comes as our nr upon k, and it will be equal to, sorry, 1 second, 4, yeah. So this comes as our V2 T2 minus T1. And we substitute the temperatures. So here K and K cancels out. So this comes as nR upon 4. T2 is our 300 centigrade. So 300 plus 273 will be 573 Kelvin minus 100, and that will be 373 Kelvin. So we get that our work done is equal to nR upon 4, and the difference will be equal to our 200. And this 200 we can cancel out by 4. This will be coming as going by 50. So we get that work done will be equal to 50 times nR, and it is given as nR. Okay, so this is given to us as n times r. Therefore we can say the fill in the blanks is equal to 50. So we get this is equal to 50. Next question. It states that a monatomic gas of mass 4u is kept in an insulated container. Container is moving with velocity 30 meters per second. If container is suddenly stopped, then change in temperature of the gas is x upon 3r. The value of x is. So here the kinetic energy of the gas will be equivalent to the, or we can say change into the heat energy, basically the conservation of energy. Okay. So we can say that conservation of energy, and therefore we can say that our kinetic energy of the gas will be equal to the heat that will be our for our gas. We get this as 1 by 2 mv square is equal to, we can write this as of n C of V times delta T. We have to find out the change in temperature, that is delta T. And so, okay, so we can write this as our half m V square. Number of moles will be over m divided by its molar mass, and C of V, and C of V is our, this is monatomic, so it will be coming as 3r upon 2 times delta T. So this 2 m and m cancels out, and this gives us capital M is given as 4, and the velocity is given as 330. So that will be coming as 30 whole square multiplied by 4 and divided by 3r is equal to delta T. So we get that our delta T will be equal to 3600 divided by 3r, and it is given as equal to x upon 3r, which gives us that the value of x will be equal to 3600. So value of x is 3600. Next question. It states that a container is divided into two chambers by a partition. The volume of first chamber is 4.5 liters, second chamber is 5.5 liters. the first chamber contains 3 moles of gas at pressure 2 atm and second contains 4 mole of gas at pressure 3 atm. After partition is removed and the mixture attains equilibrium, then the common equilibrium pressure existing in the mixture is x times 10 to the power minus 1 atm. The value of x is. So initially we have 2 chambers and 2 gases, and their respective volumes, moles as well as pressure is given for both first chamber as well as second chamber, and then mix with each other. Okay. And so that we are going to use the entire, we can say, the solution of this will be based on our ideal gas equation. Okay. We are going to use respectively for our first chamber, second chamber, and you can say then for our its equilibrium. And in this case we have to remember one thing, that it states that the equilibrium has been attained, so we can assume that the temperature has been equalized. It means temperature of first chamber, if in first case is T and the second chamber is also T, then the equilibrium temperature will also be equal to T. This we have to assume. Okay. So we can say, since equilibrium is reached, so we can assume T is equalized. So let us discuss first of all the initial conditions when both the gases are in separate chamber. So for initial condition, we have our first chamber. Let us call this as chamber 1, and we are going to use ideal gas equation, that P1V1 is equal to N1R times T, and we substitute the values. We get this as our 2 times 4.5 is equal to number of moles is our 3 times RT, and this will be coming as equal to 9, and this gives us that our value of RT is equal to 3. Now we come to our chamber 2. Same equation, but P2V2 is equal to N2 R times T, and we substitute the values. We get this will be equal to our 3 into 5.5 is equal to 4 times RT, which gives us that of RT is equal to 4.125. Okay. And now we come to our when they are mixed, that is our final condition. And for final condition, same, we can use our this as P equivalent times V is equal to nRT. Now this V will be equal to volume of first chamber plus volume of our second chamber, and we can say our V is equal to 4.5 plus 5.5, giving us 10 liters, and number of moles will be equal to our N1 plus N2. which is our 3 plus 4 giving us 7. And so we can write that our N1 RT plus N2 RT will be equal to P1 V1 plus P2 V2. And we already know the P1 V1, so this comes as 2 times 4.5 plus 3 times 5.5, and this will be equal to our, this will be 9 plus 16.5, which will be 25.5. So we get that our R okay, from here let me write it that this P equivalent will be equal to our nRT upon V, and so we get that our P equivalent will be equal to nRT upon V. And okay, I forgot to, let me write one, I missed one step here. So on the left side we can take as RT as common, that will be N1 plus N2 is equal to 25.5, and we just said that our N1 and N2 will be equal to N, so this comes as our nRT is equal to 25.5. Now we come to our P equivalent. So we can say our P equivalent will be equal to our nRT upon V, and nRT we just found out is our 25.5 and volume is our 10. So this comes as 2.55 atm. But we are given that P equivalent is equal to x into 10 to the power minus 1 atm. Therefore, we can say that value of x will be equal to 25.5. Value of x is 25.5. Next question. It states that the internal energy U, pressure P and volume V of an ideal gas are related as U is equal to 3 PV plus 4. The gas is polyatomic, diatomic or monatomic, or either either mono or dia. So here basically we are going to find out the degree of freedom, that is going to tell us about the gaseous nature. Okay. And the equation is given to us with respect to internal energy. So, and we know the relationship between internal energy and our temperature as well as our you can say degree of freedom. So we start with our basic relationship, that is our internal energy which is U is equal to N times C of V times T, that's our temperature. And from ideal gas law, we know that our PV is equal to nRT. So from here we can say that our T is equal to PV upon nR. and we substitute it in our internal energy. So we get that our internal energy, which is our N of C of V, which comes as PV upon NR, and here N and N cancels out, so this comes as our C of V upon R times PV. And we already know that our C of V is equal to F upon 2 times R. So we substitute it here, we get our internal energy is equal to F upon 2 times PV. And we are also given that our internal energy is equal to 3 PV plus 4. And we substitute value of internal energy, so we get this as F upon 2 PV is equal to 3 PV plus 4. So here, if we look this equation closely, there is one discrepancy, or we can say there is one constant term which is available here, that is plus 4. Okay. So which we can say that the constant term plus 4, it suggests a non-ideal behavior or some sort of reference point. So we can say our plus 4, it gives us non-ideal behavior. But if our this PV is very large, then this 3 PV is going to dominate our 4. Okay. So we can say our this 3 PV will be much larger than by 4. So we can say that our PV plus 4 will be approximately equal to 3 times PV, and therefore we can reformulate our equation. We get this as F upon 2 is equal to 3 times PV left side, let me write it again, this is F upon 2 PV. So here PV and PV goes away, so we get our F is equal to 6, which is nothing but our degree of freedom. Okay. And we know that our for monatomic degree of freedom is our 3, and for diatomic it is 5, translational as well as rotational, but for polyatomic it is either 6 or greater than 6. Therefore we can say this is our polyatomic. So we have option 2 is correct. Next question. It states that the volume V of a given mass of monatomic gas changes with temperature T according to a relation V is equal to K T raised to power 2 by 3. The work done when the temperature changes by 90 Kelvin will be X times R. The value of X is. So once again we are talking about the work done, and the gas here is given as monoatomic. Okay. So we start with our given relationship of volume. So we are given that our volume is equal to K times T and whole raised to power T raised to power 2 by 3. But we also know that for ideal gas, we know that our PV is equal to nRT. So from here we can say that our P is equal to nRT upon V. We substitute the volume, we get this as nRT and K raised to power 2 by 3, and this gives us nR upon K and T raised to power 1 by 3. And the standard formula of our work done, so we know that our work done is equal to integral of our dV, pressure dV, and we already know that V is equal to K 2 by 3. So we derivate it, we get this as dV upon dt is equal to K 2 by 3, and this comes as T minus 1 by 3. Therefore from here we can say that our dV is equal to, this will be 2K by 3 T times T raised to power 1 by 3 and times dt. So we get from our PdV, and pressure we also know in terms of temperature, so we can write this as our nR upon K T raised to power 1 by 3, and dV is our 2K by 3, and this is T raised to power minus 1 by 3 times dt, and this T1 by 3 and T raised to power 1 by 3 cancels out, so we get this as PdV is equal to K, and K also goes away, so this comes as our 2 by 3 nR, and dt. Therefore we can write now work done will be equal to our integral T1 to T2, and this comes as our 2nR upon 3 times dt. So everything is constant, so we get this as 2nR upon 3, and we have T2 minus T1. Difference in temperature is given as 90, so we simply substitute 90. This comes as 2nR upon 3 multiplied by 90, and this 90 goes by 30, so we get that our work done W is equal to 60 times nR, and for 1 mole we can write that this is equal to 60 times R, and we are given that this is equal to X times R. Therefore we can say that the value of X is equal to 60. Value of X is 60. Next question. It states that a diatomic gas having C of P 7R by 2 and C of V 5R by 2 is heated at constant pressure. Ratio of change in internal energy, change in our heat, and the change in work done is equal to. So it is said that it is at constant pressure. So we know that at constant pressure our D of U will be equal to N C of P and D of T. C of P is given to us, so we can write that our D of U will be equal to, and N will be, N and R will be common for both. Let me write it. This is N, and this comes as 7R by 2, and this is our dt. and our internal energy, that is our, sorry, 1 second, I wrote it, this is dq, and internal energy d of u will be equal to n c of v times dt. So once again, from here we get d of u will be equal to n c of v is given to us as 5r by 2 times dt, and our work done, that is work done dw is our pdv, or we can write this as nr times dt. So now we find out the ratio. So we get that our du times dq times dw, sorry, ratio, and we have this as our du is our n 5r 2 dt, dq is n 7r dt, and this is our nr dt. Therefore we get from here it will be 5 is to 7 is to 2. So 5 is to 7 is to 2, option 2 is correct. Next question. A thermodynamic process is shown below on a PV diagram for 1 mole of ideal gas. If V2 is equal to twice of V1, the ratio of the temperature T2 by T1 is. So it moves from 1 to 2 position, and it is governed by PV raised to power 1 by 2 is constant. So we start from there only. We are given that P raised to power V 1 by 2 is constant. Let us suppose that constant is our K. And from ideal gas, we know that our PV is equal to nRT. Therefore, from here we can say that P is equal to, you can say from ideal gas, we have our PV is equal to nRT, and we can say that our pressure P will be equal to nRT upon V. So we substitute it in the given, we get this as our nR T upon V, V raised to power 1 by 2 is equal to constant K. And from here we can say that our temperature T will be equal to, this will be coming as V raised to power minus 1 by 2, and one second, let me write it first. This comes as T, and we have this as K upon nR and V upon V 1 by 2. Okay, so in place of this entire term we can put another constant. Let us suppose that constant is our C, and that comes as a V raised to power 1 minus 1 by 2 is going to give us 1 by 2. And because C is a constant, therefore we can write our temperature is proportional to V raised to power 1 by 2. Thus we can write our T2 upon T1 is equal to V2 upon V1 whole raised to power 1 by 2. And their volume relation is given to us is V2 by V1 is equal to 2. So we can say this will be equal to our 2 times V1 upon V1 whole raised to power 1 by 2. And when V1 cancels out, therefore we get that our ratio, that is our T2 upon T1 is equal to square root of 2. Square root of 2 is option 3 is correct. Next question. It states that 1 mole of rigid diatomic gas performs a work of Q by 5 when heat Q is supplied to it. The molar heat capacity of the gas during this transformation is XR upon 8. The value of X is. So we are given molar heat capacity, which we are going to find out. It is given as X upon T. So we are going to find out molar heat capacity. So we are going to start with our first law of thermodynamics. First law of thermodynamics, and this gives us that our Q, heat supplied, is equal to internal energy and work done, and we are given that work done is equal to Q upon 5. Given work done is equal to heat supplied upon 5. Therefore we can say that our Q is equal to delta U plus Q upon 5. So from here we can find out our delta U, which will be equal to 1 minus 1 by 5 is equal to 4 upon 5 times Q. And we are given the gas is diatomic, number of moles is 1. So we can say that for diatomic gas, we have our C of V is equal to 5R upon 2, and we also know that our internal energy is equal to N of C of V times delta T. Number of moles is 1, C of V we know is of 5R upon 2 times delta T. And this delta U we just found out, so we substitute it here, so this will be equal to over 4 upon 5 times Q. Therefore we get that our delta T is equal to, this will be 8 upon 40, sorry, 8 upon 25. 8 upon 25, and this comes as Q upon R. We have to find out molar heat capacity. So we can say our molar heat capacity, capital C, is equal to our heat supplied and change in temperature. So this we get our Q, and change in temperature is our 8 upon 25 Q upon R. Q and Q cancels out, So we get this will be equal to our 25 by 8 times R, and we are given this equal to XR upon 8. So we are given that this is equal to X times R upon 8. So from here we get that the value of X is equal to 25. So value of X is 25. Next question. It states that each side of box made of metal sheet in a cubic shape is A at room temperature T. The coefficient of linear expansion of the metal sheet is alpha. The metal sheet is heated uniformly by a small temperature delta T, so that the new temperature is T plus delta T. Calculate the increase in the volume. So here we should remember that the box is in the form of cube, so when it is going to expand there will be volumetric expansion, but the metal sheet is given in terms of our alpha, that is a linear coefficient. So relationship between the two is that our beta is equal to 3 times our alpha. Okay, so we have to remember that, and we can do it otherwise also by using binomial theorem also. Okay. So let us use our binomial theorem, that is more traditional way of doing it. So we know that our initial volume that is our V is equal to A raised to power 3, and we have our linear expansion and this linear expansion, so let us say our new side is our A prime, and that will be equal to the original side length 1 plus linear coefficient multiplied by delta T, which is change in temperature. Therefore we can write our new volume, that is our V prime, will be equal to new side, which is A prime and its whole cube. So we substitute it in the terms of A, that is 1 plus alpha delta T, and this comes as whole raised to power 3. So we can write this as our V prime will be equal to our A cube, and we can expand it binomially. So this term will be equal to 1 plus 3 times alpha delta T. So we can write this as 1 plus 3 alpha delta T. Okay. And we have to find out the increase in volume, that is our delta V. So we can say our increase in volume, which is our delta V, will be equal to our new volume minus original volume. We substitute their respective. V prime is our A cube, 1 plus 3 alpha delta T, and original is our A cube. So we open it, we get this as A cube plus 3 alpha A cube delta T minus A cube. A cube cancels out, so we get our change in volume is equal to 3 alpha A cube delta T, and we get this as 3 alpha A cube, 3 alpha A cube, or 3 option 1 is correct. One is correct. So this completes all the 15 questions. for this part second for the year 2021. Thank you.